In this example, we will compute the rank of a 5 by 5 matrix. We have a 5 by 5 matrix A and want to compute its rank. We're going to do that by row reducing and looking for the number of pivot columns or linearly independent rows or independent columns. All those are the same thing for this matrix. So we're going to row reduce and see what we get. So we already start with a 1 in the top left. That is fantastic. So we can start by getting rid of everything that's below that 1. So our first step, row 2 is row 2 minus twice row 1 to get rid of that 2. Row 4 is row 4 plus row 1 to get rid of the minus 1. And same for row 5. We don't touch row 3 because it already has a 0 in that spot. So when we do this, first row remains the same. 2 minus 2 is 0. 1 minus 10 is minus 9. Negative 1 plus 4 is 3. Negative 2 plus 2 is 0. And negative 1 minus 2 is minus 3. Stays the same. Negative 1 plus 1 is 0. 0 plus 5 is 5. 3 plus minus 2 is 1. 1 plus minus 1 is 0. 6 plus 1 is 7. Negative 1 plus 1 is 0. 3 plus 5 is 8. Minus 2 is minus 4. 1 minus 1 is 0. And 1 minus 1 is... Okay, now I want to put a 1 in the next slot here. Entry 2, 2. And so to do that, I'm going to choose to take this row and swap it up to row 2. Then when I divide through by 8, I'll have exactly 1 column with fractions in it. And it'll hopefully make my life go a little easier in the future. So I'm going to swap rows 5 and 2. Give me the following. And to make the point, even if you decide not to do this step and decide to stick with the original matrix and divide by 9, you'll still get the same rank at the end as long as you follow the process through it correctly. Your matrix will look different than mine, but at the end of the day, you'll get the same number of linearly independent rows, columns, to get the same rank. As a point before, the row echelon form for matrix is not unique, but the reduced row echelon form is. So if you go to reduced row echelon form, it'll match things that you have gotten from my method doing the same process. Now let's divide the second row by 8. We'll just put the 1 in that slot where I want it. Next, since we have the 1 now here, we can use it to clear out the entire column beneath it. So we'll do that by saying that row 3 is row 3 minus twice row 2. Row 4 is row 4 minus 5 row 2. And row 5 is row 5 plus 9 row 2. The first 2 rows here do not change. And then for each of these rows, the only thing that's going to change is that we will make the second entries all 0. That's how we chose our coefficients here. And then the third column is going to change because there's a minus 1/2. The other 2 will not because there's only zeros in row 2. And that's why I put that into row 2 to make this part easier. So if I'm doing row 3 minus twice row 2, this will go up to a 4. Row 4 minus 5 row 2, I'm adding 5/2 to 1. That gets me a 7/2. And I'm subtracting 9/2 from 3, which gives me to minus 3/2. And the rest remains the same. All right. Next step, we're going to divide row 3 by 4. And just to make my life easier, I'm going to multiply rows 4 and 5 both by 2 to get rid of those 1/2, because I don't want to deal with that anymore. So row 3 is row 3 over 4. Row 4 is going to be twice row 4. And row 5 is going to be twice row 5. Which gives me the following matrix. And we can now see what's going to happen here. When I do my next step of doing row 4 is row 4 minus 7 row 3, and row 5 is row 5 plus 3 row 3, because I want to get rid of this 7, this minus 3, these are also going to go away with them. So the next step to cancel that out, row 4 is row 4 minus 7 row 3, and row 5 is row 5 plus 3 row 3 is going to give me the following, which is now in row echelon form. So I can now count 1, 2, 3 pivot 1s, or 3 linearly independent rows, or 3 non-zero rows. All of those are equivalent. Tell me that the rank of this matrix is 3. So that's an example of computing the rank of a matrix using row reduction. So it doesn't matter exactly which process you take to get here, as long as you're always doing legal elementary row operations to progress the problem towards an answer, and then you count the right things to the right pivot columns, you'll get a rank of 3 no matter how you do this. You could scramble the rows, scramble the columns. It doesn't matter as long as you follow the process correctly, you will get to a 3 at the end of this problem. So that's an example of working out the rank of a matrix with row reduction, which we'll see comes up again as we solve more types of problems in the future.